Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Idayu binti Alimun. So today I will share my research findings entitled Topological Indices in Graphs of Groups, Recent Results and Application. So this is my joint work with my collaborator, Professor Dr. Nurhaniza Samin from University of Technology, Malaysia, Johor Bahru, Johor. Okay, so this is the presentation outline for this presentation. So I will start with introduction and then explain a little bit about topological indices and what are the definitions of topological indices, graphs associated to groups, topological indices of some graphs for some groups, applications of topological indices, what are possible applications and what are the future recommendations that maybe we can apply to the application part, and then lastly references. Okay, so as you can see on the screen that we have these molecules that we convert by using graph theory to the 2D representations, which is the graph. So why we actually do on topological index? So the research on topological index actually starts with the introductions of Wiener index. So why people or chemists actually introduce Wiener index? This is because from the molecules, people want to know the physical-chemical properties. We want to predict the physical-chemical properties of the molecules, but the molecules need to converge into numerical characteristics first, because we want to know the properties of the molecules. So what is the numerical characteristics that we can focus on is topological index. That is one of the numerical characteristics. So now topological indices provide numerical descriptors that capture important structural features of molecules that serve as powerful tools for the analysis and predictions of various physical chemical properties and also biological activities. Okay, so we have various types of topological indices that have been developed based on either chemistry or mathematical perspectives. We have over than thousands of topological indices. Okay, so these are some topological indices, also types of graphs and also types of groups and rings that I have been doing so far. Okay, so we have a degree-based topological index, we have distance-based topological index, we have graphs, we have groups, and also rings. So not that many, but so we can also discover other types of topological indices. Okay, so this next is the definitions of some types of topological index. So I just said about the Wiener index just now. So Wiener index is the first types of topological index that has been discovered by Wiener in 1947, in which the concept of Wiener number, considering the path in a graph, is introduced. So the Wiener number of some paraffins are determined and their boiling points are also predicted. And then after Wiener index, so Hoytsoya reformulated the formula of Wiener index known as Wiener index of a graph, denoted by W gamma, and its formula is given in the following. So this is the formula of Wiener index involved the distance of the vertices in the graph. Okay, so this is the degree-based topological index, which is Zagreb index. So it has been introduced by Gutman in the United States in 1972. So Zagreb index is divided into two. So the first one is first Zagreb index, and the second one is second Zagreb index. So first Zagreb index is summations of degree V squared. However, the second Zagreb index, so we need to multiply degree U times degree V, where U and V are the adjacent vertices in the graph. Okay, so this is Zagreb index. So this is quite tedious and complicated, but it can be done. So we have a Zagreb index. So it involved the distance of two vertices, and we use this because this is we actually consider the counts the gamma's vertices, which one is closer to one each terminal x than the other one, and two is vice versa. So we need to consider the distance which the vertex is closer to one another. And then we have Harari index. So Harari index is the involve the reciprocal of the distance, and then drij is equals to 1 over to the distance of vertices if I is not equals to j, and 0 if I is equals to j. All right, so next is the Randic index. Okay, so it was introduced by Milan Randic in 1975. And then this formula is 1 over square root degree u times degree v. So we have also general zero for the Randic index, which involves the degree, and Sombo index also involve the degree. Okay, let's go to the graphs associated to groups. So in this presentation, I will only explaining on the two types of graphs, which is the first one is non-commuting graph, and the other one is the extensions of the non-commuting graph, which is the g-non-commuting graph. Okay, so the non-commuting graph is a graph denoted by gamma g, where the vertex set is the non-central vertices g minus zg, and two distinct vertices x and y are joined by an h whenever xy does not equals to yx, which means the two vertices the two elements do not commute to each other. So then we can have the adjacent vertices. Okay, so this is the examples of the non-commuting graph of D8. So the had groups of order 8, which means it has 8 elements in the groups, and then we exclude exclude the center because we only consider the non-central vertices. Okay, so that's why you can see here 1, 2, 3, 4, 5, 6, only 6 vertices in this graph because in the had groups of order 8 we have 2 centers. Okay, so these are the general forms of the non-commuting graph or some finite groups. So some finite groups, we have the Heidegger groups, we have generalized quotient groups, we have quasi-Heidegger groups. For this one is for the Heidegger groups is divided into two cases, which is n is odd and also n is even. So as you can see here, so the graph is actually the multipartite graph. Okay, so this one also for the non-commuting graph, but for generalized quaternion groups and also for the quasi-Heidegger groups. So also the multipartite graph. So you can just identify what is the end, and then you can get the non-commuting graph directly. Okay, next is the g-non-commuting graph. It is actually the extensions of the non-commuting graph. But this one, we need to choose a fixed element g. So we have small g here in capital letter G. Okay, so we have fixed element g. Okay, so a g-non-commuting graph of G denoted by NC gamma GG is a graph that consists all elements in the group as vertices of the graph, and two vertices x and y are adjacent if and only if the commutator xy does not equals to G and also does not equals to G inverse. Okay, so what are the elements of the vertices? So the elements of the vertices consist of all elements in G. So it's a little bit different with the non-commuting graph, because non-commuting graph, we only focus on non-central vertices. But for the G non-commuting graph, we include all the elements in the group, so that the number of elements in the group is equal to the number of elements in the G non-commuting graph. So, but the adjacency, we need to check whether the commutator of those two vertices does not equals to G and also does not equals to G inverse. Okay, so this is the general forms of the G non-commuting graphs when the fixed element is G is equals to E. Then we have the multipartite graph and the union the isolated vertex. So we have isolated vertex E, and also isolated vertex A n over 2. So divided into 2 also, and it's odd and so n is even. So if you can see, as you can see in this slide, what is the difference between the non-commuting graph and also the G non-commuting graph? So if you construct the non-commuting graph, you only, for the Heidegger groups, you only get this one. So this side only, so it does not have the isolated vertex. Okay, so but for G non-commuting graph, there is a isolated vertex here, which is E. This one is E and A n over 2. Okay, so this one is actually the center of the group. Okay, so we can actually conclude that the g-noncommuting graph is actually the same as then for the fixed element G is equals to E is actually the same as the non-commuting graph, but include or union with the isolated vertex of the centers. Okay, so this one is non-commuting graph for G is equals to AIB. So this one is the fixed element. So we have the graph is complete graph of order 2n. Okay, for g-noncommuting graph for Q for n, so we have this multiple type graph union with E and union with E to the power of n. So same goes. This is similar to the header groups. Okay, so include the centers. Okay, so and then G is equals to AIB. We get the complete graph of order 4n. For generalized for the quasi-header groups for fixed element E. So also the same, we have multiple type graph union with this isolated vertices of the centers. And then for G is equals to AIB, we have K complete graph of order 2 to the power of n. Okay, so I will present on the Randic index, the general formulas of the Randic index of some graphs for some groups, which is the graph is non-commuting graph and also g-noncommuting graph, and some groups which we have these three groups, the header groups, general groups, and also quasi-header groups. Okay, so this is the results of the Randic index of g-noncommuting graph. So the fixed elements, we only choose G is equals to E and G is equals to AIB. Okay, for G is equals to E, so based on the general forms of the graph, we can actually determine the general forms of the Randic index. So it is also divided into two, n is odd and also n is even. So just if you have d to the power of d6, if let's say you have d6 and then you have n is equals to 3, so just substitute into this one and this one, you can already get the value of the Randic index. Okay, so this one is equals to n, for G is equals to AIP, for G is equals to E for generalized quotient groups. So you will get this answer for n minus 1 square root over square root 8n times n minus 1 plus n over 2. And then G is equals to AIP through n. And then theorem 11 is for the quasi-header groups. So let's say the fixed element is G is equals to E. You will get this formula. So a little bit long compared to the others because you have the power, and it's a little hard to actually simplify with and give simplified version. So this and next is a G is equals to AIP. So we get 2 to the power of n minus 1. Okay, so Estrada index. So first we need to know the definitions of Estrada index. So it's different with the Randic index and also most of the topological index, because Estrada index involved the eigenvalues. Okay, so so first we need to find the eigenvalues, and then you can substitute into the formula of Estrada index. So Estrada index is summation of I is equals to 1 until n e to the power of lambda I. Okay. So this one is the Estrada index of G non-commuting graph for D to N. For G is equals to E, you will get this answer. So just substitute the value of N and then you will get the Estrada index. Okay, so if you want to compute from scratch, you can actually, what we did was we need to start from the group itself for the group presentations, and then we come up with the elements, and then from the elements we need to construct the graph. We need to construct the graph, check the adjacency, and then so you need to compute the eigenvalue. So in order for you to determine the eigenvalues, you need to have the adjacency matrix first from the graph. So adjacency matrix, and then come up with the characteristic equations, and then you can get the the eigenvalues. Okay, and then plug in into this formula. So so these results, the general forms of these results, this is easier because you are not going to go through the hard parts. Okay, those steps are the one that you need to find out the groups and then the elements, and then you come out the graph, and then from the graph you need to come up with the adjacency matrix, and then the characteristic polynomial, and then compute the lambda, the eigenvalues. So this formula, you can actually just know the value of n. So how you are going to know the value of n is from the groups itself. So we have the hiding groups of order 2n, and then n, let's say n is start with 3. So n is equals to 3, just plug in with the odd. N is equals to 4, you plug in with this. N is even. In this case, n is even. So you will get the answer. So it's much easier and faster. So for theorem 14, this one is for g is equals to AIP. You'll get this formula. Sorry, this one is e to the power of -1. Okay, next is for the generalized quaternion groups. We have g is equals to e. So this one, and then g is equals to AIP. You will get this formula. So for quasi-divided groups, also a little bit long, you can just plug in the value of n and you will get the value of Estrada index. So same goes to the g is equals to AIB. Okay, so these are some applications of topological indices, so that maybe we can explore. From the literature review, we can see that many people are doing on the QSPR, QSAR modeling. So just predict the boiling point and other molecular structures. And then we have also complex networks, communication networks, social networks, biological networks that we can convert into the graph theory or molecular graph theory, so that then we can compute the topological indices. And then we have mathematical chemistry, graph theory, and mathematical analysis. This one is what we are doing. So imaging and extended models. So we have fuzzy graph, with graphs, and so on. Okay, so this is just examples of one of the applications, QSPR-based drug repurposing of for anti-cancer discovery. We have these two. We have this one anti-cancer drug. This one, anti-cancer drug, and then we convert into this molecular structure, so that we can come up with the graph. So we know which one is how many edges that we have, how many vertices that we have, and then we can compute the topological indices. Okay, so from the results of that paper, so the results demonstrate strong predictive capability in identifying drugs with potential anti-cancer properties. Okay, as for conclusion, the g-noncommuting graph of 3 types of groups are presented for fixed elements E, AI, and also AIP, and then the Randic and Estrada index of the g-noncommuting graph for 3 types of group are explained, and also some applications of the TI is stated for future study. Okay, so these are some references. Okay, that's all for my sharing. Thank you.